Alright, so I am starting the YouTube live stream, and as soon as it starts up, I'm going to close that window so I don't keep too many browser windows open. Alright, so I know that one is on, so I'm going to close that window. And okay, no text messages. We are about close to 4 minutes away, a little less than 4 minutes away from the start time of the lecture. What you're seeing here is my plan for today's lecture. So there are a few things that may be interesting and maybe boring to some of you. So and then I put in a whole bunch of derivations over here. We'll get back to this, and we'll also use the tablet for certain kinds of illustration. So that's the plan for today. We may or may not have a lab today, so it depends on whether I can get to this portion in the mind map. So I'm hoping some of you are taking notes. It's really kind of important, especially once you transition to a 4-year university. Trust me, that will make this class looks like pretty easy, like child's play. Of course, it also depends on which university you transfer to, who's teaching the class. I'm just saying that in general, I think a UC or a CSU upper division class is going to be at least as challenging as this class. All right, so we have 2 more minutes or so. Someone caught my attention, so I did not go out of my way to big brother, people. But someone caught my attention, and I did a little bit of surveying, and I found that some people still have not read the notes, or at least they have not accessed the notes through Canvas. That's the fact. Okay, that's what I can see. Doesn't mean those people have not been reading, because it's possible that their friends have sent the link to the HTML to these people, and they have been reading it off the link directly and not having to go through Canvas. The chances of that is fairly low, but it still exists. So, but I still want to just kind of emphasize the importance of reading the notes, like really carefully reading the notes, making all the connections, taking notes at the same time, and being present during the synchronous lecture. All of those are important. And if anyone wants me to pull up the success mind map, I'll be more than happy to do that. I think most people do not want me to do that anymore. Let's see, I'm just taking a look at the time. We got about 10 more seconds before we start. So, and by the way, the homework is graded. The key or the answer to the homework, I believe I made a video out of it, and it has been distributed through the announcement already. So if you're curious of how your design worked or does not work, how it doesn't work, I left some feedback to most people who did not get a perfect score, but not for everybody. But the solution is there. So I think one thing you can do if you want to compare your solution with mine is really just to compare the two side by side, and just kind of notice what the differences are, if there are any differences, and try to figure out whether those differences should make it does it functionally make a difference, or is it really just doesn't look the same. All right, so it is time to get started. We got 10 more seconds to go. I'm not seeing any questions in today's text channel yet. I'm just double checking to make sure that I'm on today's text channel. There we go. Very good question. Where is the video posted? So I cannot remember, so I'm gonna go check. Oh, sorry about that. There we go. So the first thing you do is go to announcements in Pro, and oh, okay, so I may not have posted that. Very good, John. Because I may not have done that, or have I done it? I cannot remember. Let me see. Since no one else has commented that I have posted it, So I'm guessing that I have not posted it, although I kind of remember that I did something like that, but I could have forgotten. That may be the case. I think I addressed everyone in that post. Yep, it is in the general text channel. I did specify at everyone, and it is the solution to the carry look-ahead adder circuit part 2. And I'm just looking at the time and the date. I cannot remember what date it was, but the time is 3 p.m. was 3 p.m. sometime. I think it's on the same day when the assignment was due. So anyway, if you want to look at the solution, you can just go to the general text channel, and the link to the video is there. And Perry, even reminded me and go like, "Hey, you didn't post the link," and then I posted the link over there. There we go. Okay, excellent. All right, so I'm getting back to today's text channel. All right, cool. Oh, it was the 10th of September, so that was 4 days ago. All right, so that was Friday, I believe. Anyway, we are gonna get started today with a continuation of binary subtraction. But before, okay, I have to open the sliding door for the cat to get out, and he's just sitting right at the threshold. Come on, if you want to go. Okay, there we go. All right. So, getting back to the mind map. Okay, so the mind map is just a way for myself to kind of get into a habit of planning ahead, what I want to talk about and stuff like that. So, previously, we talked about carry look ahead. We did a lab with carry look ahead, and I gave you the solution of carry look ahead. What we'll do today is to continue the discussion of subtraction in binary. We're almost done. We just need to look into the borrow look ahead mechanism. And then I might get into this little topic here when I took what is equivalent to this class, many years ago in 1986 at San Francisco State University. I might get into that, I may not. So today's topic would include borrow look ahead. It will also include an activity for those of you who have study groups. Now, if you're a single person, you can do it too. Okay, it's just not as fun to do it by yourself. It's much more fun, when you have a group of people. So it's kind of like the binary addition slash subtraction version of Jenga. Okay, so I'll talk about that in just a little bit. And I'm certainly hoping that we'll get enough time to get into signed representation. This is actually quote unquote self-contained. Okay, it is already sufficient. But if you combine what I have written here along with the notes, that will make it even more useful. So I'm going to get to this part. I'll get back to this part later. And then maybe we'll have enough time to talk about comparison. It's not really an interesting new topic per se. It really is binary subtraction. But we are looking at not the difference, or not only the difference, we're looking at some other things that can give us a clue of whether the minuend or the subtrahend is smaller. Okay, so that's what I have planned for today, and let's see how far we can get. All right, so let's get back into binary subtraction, and this is not for this class. I'm just going to get rid of the tabs that are not for this class. All right, so we'll get to subtraction right there. Okay, and we'll continue. So where we stopped last time, I've spent almost the entire time in the previous class um, working out I cannot remember what I did, but we didn't really finish binary subtraction, and I believe that we did talk about the b function as opposed to the c function. So the b function is to compute the single digit borrow when you have a single digit x and a single digit y. X is going to be a digit from the minuend, and y is going to be a digit from the subtrahend. So bxy is basically a Boolean expression. It is the negation of x and y to tell you whether we need a borrow or not. And there we go. Okay. All right. So given this, we are gonna very quickly talk about borrow propagation, because what we end up knowing is the structure of subtraction is very close to the structure of addition. So for that, we can refer back to some of these notes over here, but I'll give you an example. Okay, so let me switch to the tablet so I can give you an example of subtraction in base 10 first. Okay, so we'll perform a subtraction in base 10. We'll start with 910 minus 115. Okay, so you look at this subtraction, and some of you can probably do this without even using a piece of paper, right? That's actually not very difficult. But I want to use this to illustrate the concepts. So we use 0 minus 5, but the single digit subtraction, 0 minus 5 in base 10, will give us an answer of 5. And it would also need a borrow. So I'm going to put a borrow here. And then the borrow of digit 0 is quote unquote by default a 0, even though when we build the circuit, it's going to be an input pin. And then 5 minus 0 is going to be 5. 1 minus 1 is a 0. But since we have a borrow from digit 0 subtraction, so now we have 0 minus 1, which is a 9 with a borrow. And then we have 9 minus 1, which is an 8. 8 minus 1 is a 7. So 910 minus 115 is 795. So let me see if there are any questions. So if anyone has any question, now would be a good time to post those questions in the text channel. And meanwhile, I am going to label the rows. So we got X, we got Y, we got Q again, and then we got T, and then we got a D over here. Okay, I don't see any questions in the text channel, so I'm gonna continue the lecture. So X is also called the minuend, and Y is also called the subtrahend. Now these terms we have introduced already in a previous lecture. In subtraction, it is really kind of particularly important to name these terms because subtraction is not commutative. Q is the same as before. This is the single digit difference. And then T is quote unquote take, okay, which is basically the borrow bit. But I don't want to use B because B is the name of the function to compute the T. And then D is the difference. So these are the terms. So now we want to look at how things are defined. So in this case, Q is R of xi, xy. So Q of I is R of xi, yi. And if you want to use a C function to represent R, I think we might have done that already. So in C code, R of xy, so I'm going to use just int x, int y, even though they can only be non-negative integers, of a single digit. So in this case, it can be done with a single return. And we kind of talked about how we can use modular mathematics. So in this case, we are going to add the base of 10. Well, in this case, it's in base 10. And then we add x to it, subtract y from it, and then we mod the entire thing by 10 again. And that will give us the single digit result. The borrow function is defined as this, okay? So I might have said you mentioned these things already, but I'm gonna put it here. If x is less than y, then we return a value of 1, otherwise we return the value of 0, and that's the b function. I believe these things we have already talked about. So this works for base 10. So given the way we define r and the way we define b, now we can say q of I. Okay, well I just mentioned that. So the q of I is r of xi yi, and then we want to look at t. So ti plus 1 is very similar to how we did the carry. So t of I plus 1 is actually the potential borrow between xi, yi, which is, do we have a borrow when we subtract yi from xi? And then we use an arithmetic plus here to combine it with potentially a borrow when we subtract ki from qi. So qi, ki over here. So I'm hoping this is reminding you of something that we have seen already. If you replace the t with a k and the b with a c, that's exactly the same pattern as when we dealt with addition. Okay, but we'll keep this one here for now, and then we have d of I. D of I is the r of qi ti. So it's the single digit difference when we subtract t of I from q of I. That's d of I. So once again, these are how the terms are defined and how they relate to each other. So what happens to be a k or t? A k is for addition, a t is for subtraction. Oh, good catch there. That was my mistake. So I'm going to erase the k with a t and replace it with a t. Thank you. Good catch. Good catch, Terence. Very good. All right. So this is the general structure. Okay. So once again, we are relating all of these digits in a base 10 subtraction in this case with each other. Okay. So this is how we structure a multi-digit subtraction. And we just need to define what is r in this case. Now this r, this particular r here is different from the r in addition, because in base 10, it's different. But once we translate this r into base 2, then it's actually the same as the r in base 2 when we dealt with addition. So the next question is, how do we change all of this to deal with base 2, right? So that's pretty easy. And let me see if I can just copy this page, or actually I'm going to do a little better. I'm going to copy the portion that is relevant, like just this part, and put it into the next page. And we'll move it just a little bit like that. All right, exactly. So if Taka, I hope I pronounced your name correctly, is correct. All we have to do is to say get rid of all the 10s and replace the 10s with 2s. So that is entirely correct. Okay, so we take this 10, we take this 10, and replace both of those with 2s. Okay, so here's a 2, here's a 2, and this one does not need any replacement. This one, works the same way as before. So once again, now we want to do, once we have done this, we'll go ahead and make a truth table. So the truth table goes like x, y, and we have r of xy, and then we have b of xy. X, because this is binary, so x and y can only be the 0 or 1. So once again, we have the familiar values for x and y. So this is x, this is y, and then both ones. So if you do plug in the numbers, this is what we're going to get. So r is the same as before, because this r function returns exactly the same bit pattern as the r function when we dealt with addition. Now in general that is not true for any other base, but for base 2 it does work out to be exactly the same. Now what about b? Now we talked about this too. There's only one that ends up with a 1. So b of xy is defined to be not x and y. R of xy is the same as before, so which means you can look at it in two different ways. You can say it is x exclusive or with y. You can also look at it as not x and y, or x and not y. All right, so I believe this is where we kind of left off last time. So now the question is, knowing this, okay, we can now build a circuit. I mean, if you just look at the circuits, um, carry ripple adder and also the carry look ahead adder, all you have to do is to replace the b with a negation in front of the x, and the circuit is going to work for subtraction. Okay, so that is nothing new, but we do have one more thing to worry about, which is, can we replace this addition with a logical OR? That becomes the next question. So I think we might have done this already. So the question is, can b of xiyi be a 1 while b of qiti is also a 1? I believe we have talked about this. We may or may not have. Okay, so let's assume that we have not. Okay, so I'm going to do it over here. So we have xiyi, and this is a normal addition here. And now we have b of qiti. Okay, so the question is, if b of xiyi is a 1, can we know for sure that b of qiti cannot be a 1? It just feels like I've done it already, but I'll be I'll be sure. So I'm going to say this is 1 implies not xiyi is a 1, which then implies xi is a 0 and yi is a 1, which then implies q of I is a 1 because it is xi exclusive or with yi, which then implies not qi is false, which then implies b of qiti is a 0 because it is not qi, which is known to be 0 already, and ti. So regardless of what ti is, we know that if we know b of xiyi is a 1, b of qiti has to be a 0. So that works in one direction. So let's see if we can work the opposite direction. So if we know q of qiti is a 1 already, what does that imply? It implies not qiti, because that's the application of the b function, is a 1, which then implies q of I is a 0 and t of I is a 1, which then implies xi and yi, they have to be the same. And if xi, yi are the same, I believe this is something that we did already, then b of xi, yi is guaranteed to be a 0 because this is not xi, yi. So when xi and yi are exactly the same Boolean value, then one of them, okay, is going to give us a 0. So this is, I think this is something that we did already, because it just felt very familiar to me, as if I talked about this last week, not last semester. So anyway, so getting back to this. So given these two derivations, it means, we cannot have both of these components being 1s at the same time, which is very nice because now we can just replace the arithmetic addition and replace it with a logical OR. Okay, so now looking at this, you go like, wow, this is exactly like, k between, if I replace the t with a k and replace a b with a c, this will look exactly the same as the structure in addition, right? So now the bigger question is, can we use the same trick to speed up the calculation? Um, Let me see. Okay, that's all the notes that I have on my tablet. I cannot be sure. Let me double check. It is entirely possible that it was my memory from earlier, like last semester or the summer, because I taught this class as a summer class too. So that is entirely possible. I'm looking up my own videos from last week on the 9th. And oh, okay. All right. So there was a post in the text channel that we might have done it in the lecture before the 9th. So it would be this the 7th of September. All right. Okay, let me check that too, because I do not want to make an assumption. And that's one thing, that is really kind of important, especially when you're working with math, is to kind of question the assumptions. So I'm going to go back to the notes on the 7th. And indeed, that was in the video of the. Yep, okay. Yep, okay. So if you guys are interested, it is on the 7th, about an hour into the lecture. That's when we started to talk about that. So I'm going to leave it up to you guys, okay, to review the content from last Tuesday, which is a week ago. Yep. All right. All right. Let me see. Okay, so I don't see any additional text messages now, so I'm going to proceed with the current topic. All right. So we can use an OR here, and I know this part is going to be new, okay? Because so even though we can now use logic gates to do everything, we still have the borrow ripple effect, because t of I plus 1 depends on t of I, which means until t of I has settled, t of I plus 1 is not going to output anything that is correct. And then for t of I to settle, we have to wait for t of I minus 1 to settle. So we have the entire rippling effect, just like here when we talked about carry ripple. And yes, we did talk about that one. I know distinctly that we talked about that one, and I built the circuit for that. So what we'll do now is to try to use Boolean algebra and see if we can use the same approach as carry look ahead. So by now, I believe it is very important to understand propagation. And what look ahead means, okay? Because look ahead, carry look ahead that we have already basically the previous lab on Thursday was about carry look ahead, and the whole idea is we can compute all of the carry bits in that case at the same time, and everything is within 2-gate propagation from the time the P and Gs are available to the time that all the carry bits become calculated, and that's a constant time. It is not linear to the number of bits. Okay, now the complexity of the circuit is actually to the square of the number of bits, but it is not the time that is proportional to the number of bits, which is what we want, because we are making transistors smaller and smaller, so we can sacrifice complexity in terms of silicon, the transistors, and the circuitry for efficiency. We want to get things done as quickly as possible. So what we'll do here is to go through this derivation, and I'm gonna skip the derivation in between because I use about the same trick as last time. So if you kind of keep track of the tricks that I used in Boolean algebra, it's basically the same kind of trick. It's just spaced differently and so on and so forth. So d of I plus 1 eventually becomes not xiyi or not xi or yi, and then the whole thing and ti, which doesn't really quite solve the problem, but it does present t of I plus 1 in a format that is helpful to us. So this time we're going to redefine g of I and redefine p of I. In other words, the gi and pi in carry look ahead are different. Okay, so this time, the only difference is we're negating xi first. Okay, both in the definition of g and also in the definition of p. So that's actually pretty easy because, as you remember, we use a single multi-bit gate, to compute all the g and all the p terms. So all we need is, basically just have a little bubble to negate the x before at the port, for x, and we will end up with the correct g and p terms for subtraction purposes. But once we do that, okay, once we define g of I to be not xi yi, which is this part over here, and once we redefine p of I to be not xi or yi, which is the term over here, now we see something that is very familiar, okay, because if you replace the t with a k, this is exactly the equation that we saw when we talked about carry look ahead. So given that is the structure, okay, G is, by the way, G stands for generate and then P stands for propagate. So this particular pattern makes it possible to use the substitution method that we have already talked about. So we end up, having T of n plus 1 to be defined using this quote unquote insane, notation, which we have already talked about as well. I used a C++ function to illustrate the logic of how these, the big OR and the big AND are related and how to set up the loops. It looks very similar. The only difference is we have T instead of K in this equation. Otherwise, it is exactly the same. Which also means, we, in addition, no pun intended, in addition to carry look ahead, we also have borrow look ahead. It works out exactly the same way. And you can actually change your adder 3x3 circuit to become a subtractor. All you have to do is to change P and G, how they are computed. So the AND gate and the OR gate for computing G and P, you just have to negate, the port corresponding to getting X, and now you have a subtractor. It is that simple to have a subtractor, to have a quick and fast subtractor, as opposed to the borrow ripple subtractor, which is really slow because it is very sequential. All right, so let me see if there are questions. I'm hoping these things are clicking because, I am only building upon what we have already talked about. Okay, so as Richard is typing something, I'm going to make a pun here. Basically, since I just mentioned the phrase, I hope all of this is clicking. The mentioning of k of I plus 1, to refer back to how we did the p and the g terms, I suppose that we can call these clickbaits. Yes, I know it's a lame joke. Exactly. Jonathan has noticed the similarity to addition. So that is very good. Very, very good. Okay, so we are now done with binary subtraction, and it is time to move on to, let me go back to the mind map. So this is basically how I prep, for the class right before. It takes me about an hour, to really kind of think about what I want to talk about, in what order, and so on. So we are now done with borrow look ahead, and we are going to get into an activity that you guys can do with binary addition / subtraction, because now we have done both, so you can do both. Okay, so first of all, I'll give you an example of binary subtraction. I'll just work out the entire thing, okay, and then we'll get into the Jenga portion. I hope it's pronounced Jenga, because if it is a Northern European word, the J is can be pronounced as a Y, so we have Jenga instead of Jenga. All right. All right, so let's go check out my tablet. There we go. All right, so I'm going to work out an example of binary subtraction. So we're going to have 0, 1, 0, 1 minus 1, 0, 1, 1. I'm just picking some specific number here. So let me just emphasize that this is in base 2. So this way, when you read the notes, you know that we have to use the base 2 rules instead of the base 10 rules. I don't know why, but that made me think of even Yanga. Aaron Yanga. Aaron Yanga. You mean the character in Attack of the Titan? Uh-huh. I think that's Yeager, not Yanga. That's Yeager. Aaron Yeager. Alright, so we got X, we got Y, we got Q, we got T, and we got D over here. So Q is once again just the exclusive OR because we got that when we performed binary addition. So we get exclusive ORs over here. So that's pretty easy to work out. T0, by default is a 0. Okay, once again in the circuit it is an input pin, but when we are performing a standalone subtraction like this, T of 0 is 0 to begin with. So now D is the exclusive OR between those two. So we got here, and there's a 0 over here. Okay, but 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 1 minus 0 is a 1. 1 minus 1 is a 0. So neither contributes a borrow. 0 minus 1 is an overall. We have an overall borrow over here. And then 1 minus 0 is a 1. Okay, so I just worked out a very simple example of binary subtraction. So here's the Jenga slash Yanga game that when you have a study group you can play. So the idea is to remove these digits as much as possible, but we'll still be able to reconstruct the entire thing. So I'll start with an example. Okay, so I'm gonna say, okay, I'll be the first one to go with this. Okay, so I'm gonna say let's remove this bit over here. Okay, once it is removed, can we still figure out what value that bit is supposed to be? Oh, that's pretty easy, right? It's easy peasy. This is like super duper easy because we have two clues as to what should go into this place here because it is the result of 0 exclusive OR with 1, but at the same time we also know that whatever this is, exclusive OR with 0 is going to give us a 1 over here. Okay, that's easy. Okay, so next person will come in and go like, okay, I can also remove a particular bit. Okay, so I'm going to remove this bit over here. And the question is, can we still figure out, all the missing bits, given what is still remaining on the board? And the answer is, yeah, we can still do it because even though this particular 0 cannot really give us a clue of what is supposed to be here, if we know this, but we still can figure out this one because of 0 minus 1, the Q. The exclusive OR of 0 minus 1 has to be a 1. So from once we know this is a 1, then we also know this is going to be a 1. So we still have enough bits to figure out everything in this particular subtraction. So the next person is going to take another go and go like, I'm going to pick something easy. I'm going to take away this one bit over here. That's okay because as long as we know this is 0 minus 1, we know there should be an overall borrow over here. Not a problem. Okay, so we got that. And then the next person would come in and go like, I am going to get rid of this 0 over here. All right. Okay, that's perfectly okay. So the question is, how many bits can you remove until you say, okay, guys, I think we got too many bits off. Now we can't really figure out, from the remaining bits that are zeros and ones, we cannot figure out everything else again. Yeah, sure, you can definitely do that. I'll give you an example. Okay, so I'm going to remove this bit over here. Not a problem, right? Because we know whatever this is, exclusive OR with 0 is going to give us a 1. There's only one thing that you can exclusive OR with 0 to give you a 1, and that is a 1. Okay, so yeah, you can remove any bit. Okay, you can remove even a bit from the T column, right? So let me pick one to remove, and okay, so I'll pick a very easy one. So this one is pretty ripe to be picked, right? Because it's okay, because if I know Q is a 1 and D is a 1, the T in between has to be a 0, because the D digit is the exclusive OR between the key Q and the T. So if we know that Q is a 1 and D is a 1, then T has to be a 0. So you basically just pick out these bits, one by one, until you go like, okay, guys, I think I think this is it. Okay, if we remove any more bits, then certain bit positions will be ambiguous. In other words, it can be a 0 or 1. We cannot lock down, the state of every single position anymore. So this is a game, it's kind of like a mahjong, kind of like the solitary mahjong also, where you remove the tiles until you cannot remove any more tiles. It's kind of same thing like that, but it's fun for a group to do, and it will exercise, what you know about, in this case, subtraction, but you can also do it with addition as well. Okay, so this is a game that I would encourage you guys to think about. And at some point in time, probably next week sometime, I will give you the practice exam, because it's almost 1/3 through the semester, so our exam 1 is coming up. And you will see that in the previous offering of this class, all the questions in exam 1 look like Sudokus. Okay, so basically it's kind of like what you're seeing here on the screen, except I give you very few number of bits, and then you have to figure out the rest of the bits. So that's basically an application of constraints. You're basically looking at the bits that are known and utilize those as much as possible as constraints in order to figure out the missing bits. Not always. So when I give you these, examples, there's no telling what T0 is supposed to be. It can be a 1, can be a 0. You can only use the other bits to help, figure out, what T0 is supposed to be. So we cannot make that the assumption that T0 is always a 0. All right. So this is just an example, okay? And I'll give you some additional examples maybe later on. Or for those of you who cannot wait. Okay, so if you cannot wait, give me a second here. I'll give you a screenshot as an example of something that you can work on, because I think that is actually a pretty good exercise in terms of how to make sure that you understand all of these concepts and know how to apply these concepts to solve problems. Let's see. This is exam 1. All right. So I'm going to give you an example here. I will screenshot into. I'll post the screenshot into the text channel. All right. So for those of you who really want to have a little challenge, here's a challenge. So the 0, 1, 2, 3, at the top, those are just bit positions. Okay, so they are not a part of the question. The O, lowercase o and the lowercase l at the bottom, that's something that we are going to talk about next. So, so we don't know enough to solve this problem just yet. Actually, I take it back. We do. Because in this case, O is unknown and L is unknown, which means, not knowing what overflow or L flag is doesn't really interfere with, how to figure out the rest of the bits. Yeah, so this one is really challenging. Okay, at least when we are just when we have the first exposure, this one is really challenging. So if you cannot do it, cannot finish it, it's okay to kind of go like, okay, I'm gonna wait until Tech talks more about it. Okay, that's not a problem. But it is a good exercise for you to think about it first, and then when we get to the point, where we have enough information, then we can actually talk about it. All right, so I am going to comparison now. Oh, actually, we have to talk about signed numbers first. All right, so signed value representation is right here. So you can see that I'm really just going sequential, when it comes to these topics. And that makes reading ahead of me easier because if you already know where we are and we are almost done with a particular topic, you just move on to the next one. So this is the module that talks about signed representation. In other words, if we only have zeros and ones, how do we represent negative values? So that really is the question. So instead of just reading my notes, I am going to use my mind map, okay? Because I think my mind map actually represents an alternative and possibly a better way to explain sort of the same thing. So I'm going to go back to my mind map here and magnify. Actually, there's a zoom button, isn't it? Yeah, right there. So we'll zoom to 150% and only focus on this portion here. All right, so let me go back to the text channel because I think someone typed something. For this example of binary subtraction, what is the final answer? I cannot remember. So I can give you the key, later, and I'll even show you guys how to solve it. In other words, what logic to use to solve this particular problem. Now, before I give you the answer, if you give it a try, give it an honest, try first, I think that is going to help. When I do give you the answer, you go like, oh, that's right, we can do it that way. Oh, on the tablet, I actually had the answer before I started to erase the digits. So all you have to do is to kind of go back in the video recording and you will see the original form before I started to erase digits. All right. First, modular arithmetics. Okay, modular arithmetics basically means this question mark here is not the ternary operator. It is just a placeholder for whatever operator we want to talk about. It can be addition, can be subtraction, can be multiplication. So the idea of modular arithmetics is basically saying, whatever we do, we want to mod the result with 2 to the power of n, where n is the bit width of the numbers that we're dealing with. Okay, so we're only dealing with binary numbers, and if you know that you're dealing with 8-bit binary numbers, then n is 8. You basically have to mod 2 to the power of 8, which is 256 every time you perform any type of arithmetic operations. So what is the bottom line? The bottom line is if n is 3, so we're dealing with only 3-bit numbers, then 17, 9, and 1 are considered congruent. So 17, 9, and 1, because once you mod 17 with 8, you have 1. If you mod 9 with 8, you have 1. If you mod 1 with 8, you have 1. So once we consider that we're using a modular system, then these 3 values are congruent with each other. In other words, they're the same. There's no, the way we represent 17, the way we represent 9, and the way we represent 1, when we only have 3 bits, will mean that the bit patterns are actually identical. They're all going to be 0, 0, 1. So are we okay with that concept? Congruency. I believe this is a concept that some of you may have encountered already in high school, but I cannot say for sure that everybody has been exposed to the concept of congruency. So you guys will have to tell me, okay, whether my assumption is correct or not, that you have already encountered the concept of congruency. Okay, well, that's fine. So now we are establishing the concept of congruency of, we basically have to remember to mod whatever value that we're dealing with 2 to the power of n, and n is the number of digits that we are using in base 2. Is that okay? Does everybody now understand why 17, 9, and 1 are considered equivalent to each other or congruent to each other when we only have 3 bits to represent values? Because they all have a remainder of 1, exactly when you mod with 200. In this case, it's mod with 8. Okay, very good. So in general, okay, for all x as a natural number, x is equivalent to x mod 2 to the power of n. So that means it means a few things. It means what we have seen here, but it also means there's an infinite number of values that are congruent to each other given a particular width, which is n in this case. No, it's not mod 2. It's mod 2 to the power of n. It's not mod 2. It is mod 2 to the power of n. So if I want to spell this out clearly, we are just going to put parentheses around 2 to the power of n. Yes, so we are dealing with base 2 because what we are going to talk about only works in base 2. So within the context of signed representation, it is all only relevant when we're only using base 2. Because the idea is, how do we represent something that is negative when all we have are zeros and ones? We cannot have a little sign in front of a particular number and say, oh, by the way, this is a negative value. Nope, we don't have that sign. Okay, we don't have that leading minus to indicate what is to its right hand side is the magnitude, but it is pointing to the left hand side on the number line. We don't have that option because everything has to be a 0 or 1. We will have an extra bit. Well, that's an idea, is to use an extra bit to indicate the sign of what is the rest of it. The problem of that approach is you cannot reuse the adder and the subtractor that we have already talked about. That's the problem, okay? Because we want to reuse, the circuitry that we have already worked out, which is the carry look ahead, circuitry. We want to reuse it, okay? So that it will even work with numbers that can be signed, okay? Numbers that can represent negative values. So that's why, we are not going to use an extra bit just for the sign, okay? So next, we're going to talk about the negation. This is arithmetic negation, okay? It is just negative minus x, okay? And over here, we have, 0 minus x, okay? So I want to see if everybody would agree, minus x, or the arithmetic negation of x, is really the same thing as 0 minus x. Do we have a question about that? Just the first row. I think that's a pretty well established fact, okay? Very good. And from the first row to the second row, it starts to look a little weird, right? Because, 0 minus x is now 2 to the power of n minus x. That is because I'm not using equality here. When you use equality, you're talking about the values being the same. But what I have here is the congruency or equivalence, okay? In this case, it's congruent within a modular 2 to the power of n system. So this part here, when we change the 0 to 2 to the power of n really has to do with this particular rule to say that in general x is congruent with x mod 2 to the power of n. So basically I can add as many 2 to the power of n to x and the sum would still be congruent with x itself. So are we okay going from the first row to the second row? It's not okay. So the same is very colloquial, so we can only say that they are congruent. They are equivalent when we only have n bits. Okay, so when we're only given n bits, the way we represent 0 minus x will be the same way that we represent 2 to the power of n minus x. That's basically what the triple bar is saying, is the representation is going to be the same. they use exactly the same representation as a base 2 number that only has n bits. So are we good with that? All right, very good. So this is, another way to look at congruency is they have the same representation. So when we translate everything into zeros and ones, the state of the transistors and whatnot, the way we represent 0 minus x and the way we represent 2 to the power of n minus x will be identical. Okay, they basically would use the same bit pattern when we only have n bits, to represent those values. Because the same representation can be used to represent different values when we have a fixed number of digits. All right, so from the second row to the third row, I think that one is an easy one, right? Because from here to here, all I'm doing is subtracting one first and then adding one back. So it really should not be a problem, going from the second row to the third row. Are we good with the second to the third row transition? Cool, all right. And from the third row to the fourth row, that's just using commutative rule to kind of move things around a little bit. So all I did was to exchange the +1 and the minus x and then put parentheses around the first 3 items and then separate the +1 to be outside of the parentheses. So are we good with from the third row to the fourth row? All right, very good. And then from the fourth row to the fifth row, suddenly we go like, what is that, right? What is that tilde thing, right? Tilde thing, the little squiggly thing. That is bitwise not. Okay, bitwise not is the same thing as a multi-bit negation gate. Okay, it does exactly the same thing. So why can we go from here to here? That is the question. So the first thing we want to observe is 2 to the power of n minus 1 as a binary number basically have just n ones. Okay, what does that mean? So let's add to this. So what this means is if you look at, let's say n equals to 3, okay? So if n equals to 3, then we are looking at 2 to the power of 3 minus 1, which is 7. And 7 is 111 as a base 2 number. And this time I can use subscript 2 to be fancy. There we go. Is that okay? Does everybody understand? When I use this specific case when n equals to 3, in other words, we're only dealing with 3-bit numbers. 2 to the power of 3 minus 1, which is 8 minus 1, is 7. 7 is represented as 111 as a binary number because it is 1 plus 2 plus 4. Are we good? Okay? Are we okay here? Excellent. Okay. So the next one is for any bit b, so b is a single digit as a binary number, 1 minus b is the negation of b. Can you buy that? Are you sold? This is what I'm selling. Are you sold? Okay, very good. So this is really significant because what it is doing is it is changing an arithmetic operation, which is the subtraction, into a Boolean operation, which is the negation. All right. Okay, so I got a text message from somewhere else, but it's okay. I can ignore that for now. Okay, so are we okay with this one? Jonathan said it's okay. What about the rest of the class? And once again, you don't have to use the text channel for the entire class. You can always direct message me if you need a little bit more time or you want me to clarify certain things. All right, so looking good, makes sense. Okay, so moving on to this slide then. Okay, for n-bit numbers x and y, so x is an n-bit number, y is an n-bit number. Y equals to the bitwise not of x is basically saying, okay, this is a quantified statement. All it's really saying is let's limit the range of I. That's all it's saying. Okay, so I is going to be 0, 1, or 2 when n equals to 3. So all it is saying is this is how we perform bitwise not. Is each individual bit is negated. Let me give you an example. So, um, let me see how I'm going to do this. I don't really need to use LaTeX for this purpose, but I'm gonna do it anyway. So the bitwise NOT of 1011 in base 2 is going to be 0100 in base 2. Okay, do you see how each bit position is negated? How the first one, the most significant one, becomes a 0, the second most significant 0 becomes a 1, and then the two remaining ones become the zeros. So are we understanding what I mean when I say bitwise NOT? We apply negation to every single position of a multi-bit number. Yep, exactly. It's flipping the bits, but it's flipping all the bits at the same time. So that's kind of what it is doing. All right. So the next one is really just a definition. It's just defining C1 as a function to be the bitwise NOT of the argument. So C1 of x is bitwise NOT of x. All right. So Jonathan said in the quantify statement, why don't you have a? Oh, I don't have a close because I forgot to use a backslash to escape the close. Let me see where the close is supposed to be. Oh, okay. Yeah, it's there. So if you don't understand the quantified statement, it's okay. It's not really a topic for this particular class, which is interesting. I'll explain that later. Yes, so my watch just buzzed me, which means it's time for row taking, your favorite activity, because you're going to ask, what is Tech going to use today for row taking as a word? And I'm trying to find out where I hid that. There we go. The first one. There we go. All right. So this is for today. And let's check out the answer. The answer is flags. F-L-A-G-S. I'm going to type it in the text channel. Flags. There we go. And I'll release it. You got about 9 minutes or so to type that in. Alright, so I'm going to move this out. And I'll keep an eye on. Oh, it's still locked. Oh, why is it still locked? Oh, I got the wrong time. That's it. Huh. Okay, so I got. Okay, give me a second. I'm going to change the time. My alarm is not synchronized with the time of the activity. So let me change it to. I'll give you guys 10 minutes. It's 58 right now, so it's going to be 10:08 a.m. And save. There we go. Okay, go ahead and refresh and see if you can get into it. Very good. Okay, so I'm just starting to see people getting it done. Cool. Nice. All right. Okay, so with that taken care of, we're going to go back here and talk about, okay, so now that C1 is explained, so we'll go ahead and define C2. C2 is also known as 2's complement. So the 2's complement of a bit pattern x is the 1's complement of the bit pattern x plus 1. You go like, well, haven't we kind of talked about something like this already? Yep, it is really just the last row of what the negation of x looks like. So this is interesting because we took something, the arithmetic negation of a particular bit pattern, and we changed it so that we can now implement it using a binary negation, multi-bit negation, and a plus one. Now we know how to do a plus one already because we talked about carry look ahead, those are the adder thing. So now we know how to take the negation of something, which also means we now know how to represent a value, a negative value, because the bit pattern, this is just a bit pattern, okay? The 2's complement of a bit pattern is by itself a bit pattern. All right? All right, so let's take a look at some examples. Okay, we got 20 minutes left, and I think we will have enough time to talk about these things over here, because that's all you need to know for the lab, even though the module will further explain the rationale behind all of this stuff here. So let me take a look at the text message. Yes, it does tie to the number wheel concept in the notes. That is correct. So what I'm going to do is I will show you a few examples first of using 2's complement and also the way it works. Okay, so let's switch back to the tablet because I'm going to use that to give you some examples. All right, so we're going to say n equals to 3. Oops, wrong tool. There we go. So we're going to say n equals to 3, and we want to look at, say, -2. Okay. Can I resubmit the role taking quiz in Flex? Okay, so we'll do this after class. Okay, so remind me to handle this after class. So we want to look at -2. So -2 is -1, 0 in base 2. Okay, so far so good. But I'm using the arithmetic negation operator here, which is not something that we want to use because we want to translate everything into a binary operation. So we go like, but according to the equations in the mind map, this is the same thing as really just the negation of 0, 1, 0 in base 2, because now we have to be careful because we have to remember to use all the bit positions. So even though the value of bit 2 is a 0, which normally we don't write because it's a leading 0, but in this case it is important because when you perform a bitwise NOT, that 0 is going to turn into a 1. So now we say this is this whole thing and then plus 1. Okay, and then we look at this and go like, okay, that's pretty easy because a bitwise NOT is really just flipping all the bits at the same time. So that means we have a 1, 0, 1 in base 2 plus 1, and that becomes 1, 1, 0 in base 2. Oh, so that's how we represent -2. The value of -2 is now represented using 3 bits as 1, 1, 0 in base 2. That is kind of cool, right? So the next question is, how do we know this works, right? If we negate, 1, 1, 0 in base 2, do we get back, as 2 itself? Is 1, 0, 0, 1 base 2 or 1, 0, 0 base 2? I'm not sure about that. I mean, I'm not sure what it's asking. How do we choose the n? Oh, this is just I just chose n to be 3. N is the width, the number of bits that we are using to represent values. So it's given. It is given in this case. All right, so if n was 4, then would be, yes, there would be 2 leading zeros. That is correct. Jason is correct. You do 101 in base 2 plus 1, but wasn't sure how to add the 2. This is okay. This 2 is just meaning that we are dealing with base 2. It's a suffix. It is not a part of the number. Because the 1 should be represented as 001 in base 2. Well, 101 in base 2 plus 1 is 110 in base 2. All right. Okay, so here's the next question. If we were to see the answer alone in a different situation, how would we know to recognize it as -2 and not 6? Very good question. Okay, so Ashton just asked a very, very good question. So I'll answer that question in just a little bit. Okay, but remind me to answer if I forget to do it. Okay, so right now I'm going to say, what about if I take the negation of 110 in base 2? What is that going to look like? Well, we say, taking the negation is the same thing as taking the bitwise not plus 1. Okay, and a bitwise not in this case is going to be 001 in base 2 plus 1, which is 010 in base 2. Oh, so we got it back. Very nice, right? So now let's go back and answer Ashton's question. Okay, so let me open a new slide because it is kind of important to establish the context in the new slide first. So if we just look at 110 as a bit pattern, the question is, what value is it representing? Is it representing -2? Is it representing 6? Or is it not a value? So my answer to this question is, why do you care? Why do you care if it is just stored somewhere in the memory of a computer, or it is stored in a register, which we'll talk about in, by the time we get to mid-semester, we'll talk about registers. So anyway, if 110 is just stored somewhere within a computer, why do you care whether it is -2 or 6? It doesn't make any difference. It really does not. It could be just a little it's a very small portion of a picture in monochrome, a black and white picture. So for all we know, we don't really know what 110 is representing. It may not even be representing a value, right? So we don't ask that question. Okay, that's the funny thing. Okay, we just don't ask that question. So now we're gonna do something that is a little bit funky, okay? Because we have just talked about negation, so now we're gonna talk about something that is a little bit funky. And let me go back to the mind map because it is in the mind map, and I need to go find right there, mind map. So now we're gonna move on to comparison. Okay, so comparison, as it turns out, is really just subtraction, and we are just interpreting certain portions after a subtraction so that we can see whether the minuend is less than the subtrahend or not. Okay, all right, so that sounds kind of like, what did you just say? Right, okay, so we'll go ahead and perform a few examples. So we're going to use 110 because that's one thing that we have talked about already. Let me switch back to the tablet. So we're going to use 110 and then we subtract 001 from it. Okay, and in this particular case, the T0 is assumed to be a 0 over here. All right, so we'll go ahead and perform the subtraction. It's not really that complicated. We can do it in any way. We can do it, just go like, okay, this row is the exclusive OR of the previous two. 0 minus 1 end up with a borrow over here. And then 1 minus 1. Okay, now we can actually finish the last row. So 1 minus 0 is a 1. 1 minus 1 is a 0. Neither of these subtraction is contributing a 1 to this borrow here, so it's going to be a 0. 1 minus 0 is a 1, 1 minus 0 is a 1, and we have an overall borrow of 0 because 1 minus 0 and 1 minus 0 does not contribute a borrow over here. Oh, these circuits are really easy. Based on what we have already talked about, the carry look ahead adder, This one is just adding some additional circuitry to it. Think about buying a car, okay? So you have a base Camry already at this point. So we're going to make the Camry a limited edition. That's all. Okay, it's the same transmission, it's the same engine. We are just making a gold emblem, okay, and we're gonna put on some leather seats, okay, maybe tinted windows, and then we got everything. Yes, we are turning a V6 Camry into a Lexus, and then we sell it at a whole different price point. That's all. Sunroof, yes. The stitches, don't forget the stitches of the leather seat. Gotta have the highlight, red color on black, or something along that line. All right. Yeah, you might need to delete 2 doors in that case. Um, all right, so getting back to this example. So what are we talking about here? So there are a few things, okay? So let me look at the time. All right, so a few things. So the first thing is going back to the mind map. So getting back to the mind map, we have a few flags that we want to talk about. So first of all, there's the B flag. Well, the B flag is actually just T of n. Remember, n is the number of bits. So in this case, in this example, n equals to 3 because we're dealing with 3-bit numbers. So B flag, the B flag, not B flat, okay? B flag is really just T3, which in this case is a 0. Is that okay? Does everybody understand what the borrow flag is after a subtraction? It's basically the overall hanging, borrow flag or borrow bit that doesn't go into a part of the difference. All right, cool. Okay, Daniel, does that mean you want to pause? Because that looks like a little pause symbol. Yep, it is. Are you pausing me? Okay, I'm not really sure how to make what to make out of the pause icon. All right. All right. So, okay, so that is the representation of whether or not there is a remainder. No, 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 no. This has nothing to do with remainder. Oh, you guys can pause me. I mean, that's okay. But in addition to pausing, I would like to know, what I can do to help. Okay, so I don't have a problem with when people say I need a little bit more time because I tend to go a little fast until people say, no, hold on, you're going a little too fast. All right, so that's just the definition. Okay, it really is just the definition after a subtraction. The B flag is T of n, and n is the number of bits that we're dealing with here. So that addresses this particular definition. So now we're going to address a easier definition, which is the S flag. The S flag, which is the sign flag after a subtraction, is, okay, so I'm going to write here, the sign flag is the most significant bit of the difference. So in this case, it will be this guy here. So it's going to be a 1. Okay? So do we have any questions about the definition of the sign flag after a subtraction? It simply is the most significant digit of the difference. That's all. So instead of saying D2, we give it a fancy name. Now it is Camry. It is ES330 instead of a V6 Camry. That's all. It's just a fancy name. All right. I'm not sure what you mean by the leading 0. So does the B come from the last borrowed number? No, this is B, and this is sign. Nope, there's no extra 0 because when we perform a 3-bit subtraction, the difference can only have 3 bits. The difference must have the same width as the minuend and the subtrahend. It cannot have any more bits than x and y. All right, so we go back and take a look at 2 more definitions, and we'll be ready for the lab. All right, so this is the O flag. The O flag looks complicated, okay? But it does boil down to something that's really kind of simple. Okay, so we look at the O flag here, and in this particular equation, remember this is in the context of something that is base 2 or Boolean, which means whatever looks like a multiplication is conjunction, and then the plus is a disjunction. Yeah, that looks like me. So if I am a mini me, so that means there has to be a super me somewhere. I need to go find my super me because I know I am the mini version of me. So anyway, are there any questions about the O flag or how it is defined? It really is just taking a look at the most significant digits. Okay, so we are looking at this digit here. Oops, let me switch back to the tablet. So we are looking at the most significant digit of the minuend, the most significant digit of the subtrahend, and also the most significant digit of the difference. And then in this case, O is not 1 and 0 and 1, or 1 and not 0. Oops, bad handwriting here. 1, not 0, and not 1. And that turns out to be a 0 or 0, which is also a 0 in this case. That's just how it's defined. Okay, the rationale of the definition, we'll talk about it on Thursday, but at this point we just need to know this is how overflow is defined. All right, so this one is going into this one over here as well as this one over here. This 0, oops, is going to here and here. And then finally this one is going to here as well as here. All right, so it's still a Boolean expression. It just has some kind of funky negation while we perform the conjunction. The O flag is the overflow. That is correct. Very good. So that's telling me someone is reading ahead of time. That's nice to know. And finally, we have the L flag. So the L flag is the exclusive OR between the sign and the overflow. So let me just say here, the L flag. L stands for less than, by the way. Is the sign flag exclusive OR with the O flag. The sign flag is a 1. The O flag is a 0. So that means the result of the L flag is a 1 in this case. Are there situations where borrow and overflow are different? Yes, there are quite a few occasions where they can be where they're different, and hence the necessity of the O flag, because if the O flag and the B flag are the same or the negation of each other, then we wouldn't need the O flag. So we'll talk about those special cases. Your lab does not actually ask you about those special cases. So right now we have all of these definitions, and I'm going to answer. We got 1 minute left, so I'm going to answer the earlier question that somebody asked of. So when we look at 110, should we look at it as -2 or should we look at it as -1? -2 or 2, sorry. So 110 is either a 2 or a -2 if we choose to interpret it as an integer value. So here is why it is important. If we look at 110 as -2 and 001 is always a 1, then -2 is less than 1. That is what the L flag is indicating, is whether the minuend is less than the subtrahend if we look at both of those numbers as signed numbers. Okay, so the L flag says, yes, -2 is less than 1. So what about the 6? Okay, what if we choose to look at 110 as 6, which is unsigned, and how do we confirm that 6 is not less than 1? That is the job of the borrow flag. So the borrow flag being a 0 in this case means if you choose to look at the minuend and the subtrahend as unsigned numbers, then the minuend is not, because there's a false over here, so the minuend is not less than the subtrahend. Now, the S and the O flag, they're not really that super useful by themselves, but they are useful once you combine both of those into the L flag. So the L flag is conclusive to tell you whether the minuend is less than the subtrahend if we look at those bit patterns as signed bit patterns. All right. Is that map posted anywhere? Nope, it is not. I can save it and post it, or you guys can just kind of do a little screenshot and paste it into your notes. Either way works. I mean, I can save it now and post it. So let me save map to. I'm gonna put it into the temp folder. I don't need it back. I mean, this is really just rough notes for myself of what I want to talk about today. So B is for unsigned and L is for signed. That is correct, Matt. And both are indicating whether the minuend is less than the subtrahend. So B is indicating whether the minuend is less than the subtrahend when we have unsigned numbers, and then the L flag would do the same, but when we are dealing with signed numbers. And I hope those concepts were discussed in CISP360. So you have signed and unsigned integers. I'm uploading the mind map for today. You still have to install FreePlane in order to open it, because otherwise it really is just an XML file. But once you install mind map, FreePlane, you can go ahead and open it. It would have the same content as what you saw today. And as Matt is typing, I'm going to open up the lab for today. Yeah, you guys can keep typing questions. I'm just taking care of the clerical stuff to open the lab. And it has a passcode of flags, same as the row taking word. And then we'll make it due today at 1:20 p.m. Alright, so Matt typed, one only considers only positive integers, and that would be the unsigned numbers, and the other one would have positive and negative. Yep. It is mostly used to increase the bit length you can use when you're doing something that calculates something that would only be positive, like distance. So I'm guessing the unsigned is only good for counting. So you can look at one as natural numbers or counting numbers, and then the other one would be actual integers, because it can go in both directions. So most of the time when we want to go through a loop and we want to visit a particular element in an array, those would be situations where an unsigned would be useful, because you cannot have a negative index in C or C++. In other languages, sometimes yes, you can actually have negative indexes, but not in C or C++. So it would be relevant to use a unsigned variable in that case. Yep, so the lab is released. You guys can go ahead and get started. Even though it's not 10:30 yet, once I answer all the questions, I'm gonna stop live stream and then take a break, and then I'll be back to answer questions for this particular lab. But the mind map is going to be useful because it actually just summarizes everything that we talked about today, in a very concise way. Okay, Matt is still typing, so I'm gonna, and Nathan too. All right, so Matt types, but it is it also increases the amount of memory available. I'm not sure if that's the correct term, but it frees up space you would be using accounting for negative numbers. So to answer the question, it's you still have the same number of distinct values that you can represent. All you're doing is shifting that range. So instead of, I'll give you an example. In using only 3 bits, if you use unsigned, you go from 0 to 7, but if you use signed, you go from -4 to 3. So basically, in signed interpretation, half of the values that can be represented using the bit pattern would be negative values. So basically, you split it, half and half. Half would be negative, and the other half would be non-negative. Ben is asking, did I post the code? The answer is yes, I did post the code. It was flags. And then Nathan said, yeah, I like how you use it to display every topic to be discussed. Yeah, I think it depends on the person, but I personally I really like to use free playing. Also because it can display equations and stuff like that. It really is handy for a class like this. All right, cool. And I don't see any more typing or questions, so it's time for me to stop the screen share. So I'm gonna close